In this video, we are going to talk about the topics in chapter 19, which have to do with aldehydes and ketones. Understand that when it comes to aldehydes and ketones, both functional groups possess a carbonyl group. The carbonyl group, as you can see in these green boxes, is specifically a carbon atom, which I am just writing in, which is double bonded to oxygen. In the illustration that we have in the top right corner, next to what represents an aldehyde and a ketone, you can see that the carbonyl group is specifically a polar covalent bond. And it is polar covalent because of the electronegativity difference between carbon and oxygen. Remember that in a polar covalent bond, we can illustrate these electronegativity differences with the symbol delta, which I'm circling it at the moment. And delta plus signifies that the carbon atom is electropositive compared to the oxygen atom. Now, when it comes to an aldehyde, we need a carbonyl group that has specifically a hydrogen atom to one side, and in our group or the rest of the molecule can be H, aryl, or alkyl in nature. When it comes to a ketone, understand that the two R groups that are bonded to the C double bond O must be alkyl or aryl in nature. Remember that aryl refers to an arene, in other words, a benzene ring. Now, understand that these functional groups are actually important in biology and in industry. To give you examples of molecules that have aldehydes and ketones in them, as you can see in the bottom left corner, we have formaldehyde. And formaldehyde is actually utilized as a preservative. So if you have taken a course like anatomy, you might have experienced like a pungent odor around the specimens that are preserved in anatomy, which is a human body, and it is because of the formaldehyde. Acetone is an example of a ketone. It is actually the simplest ketone and is utilized as a solvent. And we can find it in paints as a solvent or even in nail polish remover. Now we are going to discuss the nomenclature rules for these functional groups. There are 4 discrete steps that are utilized in order to name aldehydes or ketones. And understand that these steps are not going to extend too far away from how we know to name alkanes, alcohols, and other functional groups that we have discussed previously. The first thing is to identify and name the parent chain. Then we are going to be identifying the name of the substituents or the side groups. We're going to be assigning a locant or a number to each of the substituents. But note, for ketones, a locant for the C double bond O is also required. And lastly, we are going to assemble the name alphabetically, in which we are going to put as a prefix the substituents, and the last word is going to be the parent chain name. Let's first discuss the nomenclature rules for aldehydes. So when it comes to aldehydes, as you can see, the first rule is going to be identifying the parent chain. And for that, we are going to be locating the longest carbon chain in the alkane name for it. We are going to change the E ending by an AL ending. So for example, the skeletal structures that we have in the following slide, if I highlight the longest carbon chain will be 1, 2, 3, 4, 5 carbon atoms in a row. The alkane name is going to be pentane, and we're going to replace that E by Al. So the name of this aldehyde is going to be pentanal. Now, when we are numbering aldehydes, understand that always, the carbonyl is going to be carbon 1. So that's why for aldehydes, we don't need to put a locant for the aldehyde because the carbonyl carbon is always carbon 1. So when we name the following aldehyde, this is going to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Now, here we have as a substituent, which I'm highlighting in yellow, a single line, which we know that that represents a CH3. That means that our substituent here is going to be a methyl group. So when we look at the final name for this molecule, we're going to put the parent chain at the end. And then as a prefix, we're going to put the location. And then the name of the substituent. Now, understand that if you have a chiral center, specifically only one, in an aldehyde, you can put in parentheses at the beginning of the name the configuration of that chiral center. If you have more than one, two or more, you need to give the location for the specific chiral center. So for the molecule that we have as an example, as you can see here, our longest carbon chain is going to be 1, 2, 3. I'm going to highlight the substituents in yellow, which this one is a chlorine, this one is a phenyl group, so the chlorine is chloro. When I number, this is 1, 2, 3. That's where propanal comes from. Remember that those substituents need to be placed in alphabetical order. So when we compare P and C, C comes alphabetically first. That's why we have first the 2-chloro followed by the 3-phenyl group. And then in parentheses, because we only have one chiral center, we put it in parentheses at the beginning of the name. Now, understand that if we have an aldehyde motif that specifically is a C double bond O bonded to hydrogen, which represents the aldehyde, but that is right next to a ring system that is known as a carbaldehyde. So when we're naming it, as you can see, the last word is going to be carbaldehyde, and then the cyclic system that is attached to our carbaldehyde, that's the name that we're going to put as the prefix of the word carbaldehyde. Understand that the IUPAC also recognizes the following common names as parent chains. So as you can see, we have formaldehyde, acetaldehyde, and benzaldehyde. Now we are going to go through the nomenclature specifically for ketones. When it comes to ketones, as you can see, we're going to name the longest carbon chain by replacing the E in the alkane name with "-one", because for a ketone, since that is the functional group, the ending is going to be "-one". Now, in this molecule, as you can see, our longest carbon chain is going to be 1, 2, 3, 4, 5 carbon atoms in length. So if we write the alkane name is pentane, we erase the E and we put "-one", pentanone, that's where this word comes from. And as I mentioned previously, when we are numbering our ketone, you're going to number the carbon chain starting from the end near the carbonyl group. And we have to indicate its location. So that means that we're going to number this molecule as 1, 2, 3, 4, 5. We have to give the location, so that's where the 2 comes from. We need to give the location of the carbonyl group for a ketone. Remember that for aldehydes we don't. And in this molecule we have one substituent, which I'm going to highlight in yellow, and that is a CH3 group, which that is called a methyl. And that's why for this molecule we have the location of our substituent, the name of our substituent, followed by the location of our carbonyl within our parent chain. So the name of this molecule is 4-methyl-2-pentanone. Now, understand that when we have a ring system, that it is a cyclic ketone, we don't need to number, okay, specifically the carbonyl carbon within the ring system for the ketone, okay? So when it comes to this, as you can see, if we compare the cyclic alkane cyclopentane to the corresponding ketone, if we have within the ring system a C double bond O, as you can see, we just, in a way, if I zoom in into the name, all we are doing is taking off the E and putting "-one". So this is cyclopentanone. Now, understand that if there were substituents in our cyclic system, then understand that the carbonyl carbon then is carbon 1. So that's the only instance for a ketone that carbon 1 is the carbonyl carbon, only in a cyclic ketone. And then we are going to number the cyclic ketone clockwise or counterclockwise to give the substituents the lowest number. So let's say, for example, if I have an ethyl group here, I just drew it in. Then in this instance, we are going to name our the cyclic ketone 1, 2, 3, 4, 5. And that means that to the name with the substituent that I added, this is going to be 3-ethyl cyclopentanone. And understand that only cyclic ketones don't get a number for the C double bond O. For straight chain ketones, we must give a locant to the C double bond O. Now, understand that the IUPAC also recognizes the following common names as parent name for ketones, including acetone, acetophenone, and benzophenone. Now, understand that if you have an aldehyde and a ketone in the same compound, the ketone gets the name oxo, What does that mean? That if we have an aldehyde in the ketone, the aldehyde group will get the priority in numbering. So if we look at the example that we have in the bottom, and I number, carbon 1 is going to be the carbonyl in the aldehyde. This is carbon 2, 3, 4, 5, 6, 7. Because we have 7 carbons in the molecule, that's where the heptanal comes from. Then we're going to have 2 substituents, which I'm going to highlight in yellow. One is the chlorine, and the other one is going to be the C double bond O. The chlorine is going to be known as a chloro group, while the C double bond O is known as an oxo group. We still have to put them in alphabetical order, so that's why the correct name for this molecule is 4-chloro-5-oxo-heptanal. Now let's go over the preparation of aldehydes and ketones. This is basically a review. So, the first thing that we're going to review is how to make an aldehyde. And remember that for aldehydes specifically, we have several ways in which we can prepare them. So we can actually prepare aldehydes by oxidizing primary alcohols. Remember that one of the main ways that we know how to do this is by taking a primary alcohol and reacting it with PCC, okay? The CH2Cl2, that is just going to be the solvent. Now, remember, if you suggest a strong oxidizing agent, that takes it to a carboxylic acid, so that is different. So in order to form specifically the aldehyde, we need mild oxidizing conditions, like PCC, okay? And as you can see, that's the most common way to do it. Another way in which aldehydes can be prepared from specifically an alkene is by the molecule undergoing ozonolysis. But if ozonolysis is utilized, remember that the aldehyde must be formed if in your alkene you have vinyl hydrogens, meaning that directly to the carbon-carbon double bond, we must have hydrogens. So when ozonolysis proceeds, we will be able to form then the aldehyde motifs. As you can see, I circle those areas in red. Understand that aldehydes can also be prepared from hydroboration oxidation of terminal alkynes. And as you can see, this results in an anti-Markovnikov addition of water across the pi bond, followed by the tautomerization, and that's what forms the aldehyde. So in this molecule, if I number the carbon atoms, and this is carbon 1, and this is 2, and carbon 2 is attached to the R group, this is carbon 1, this is carbon 2, and then as you can see, because it's an anti-Markovnikov addition of water across that pi bond followed by the tautomerization, that's what results in the formation of the aldehyde. Now we're going to proceed to talk about the preparations of ketones. So ketones can be prepared from secondary alcohols. Now, there are a variety of oxidizing agents that can be utilized to make that ketone, but understand that secondary alcohols only have one result, which is the formation of a ketone when oxidizing reagents are utilized. It doesn't matter if you utilize mild or strong oxidants, they both result in the formation of a ketone. So remember, because ketones do not undergo further oxidation, that's why there is not a particular or specific oxidant that is going to be preferred. So for ketones, you can utilize the reagents that make chromic acid, or you can use PCC to form the ketone. Ketones can also be prepared by ozonolysis, but remember that if a ketone is going to be prepared by ozonolysis, remember that it needs to be a tetrasubstituted alkene that when it's cleaved, then that's going to result a ketone. So in this case, those R groups need to be aryl or alkyl in order to result in the ketone. Ketones can also be prepared by an acid-catalyzed hydration of terminal alkynes. And as you can see here, is because in this reaction, we have a Markovnikov addition of water across the pi bond, and that is followed by the tautomerization to form a methyl ketone specifically. So this is, again, another way that we can make a ketone. Lastly, another way that we can prepare ketones, and this is specifically attached to aromatic rings, is through the Friedel-Crafts acylation reaction. So when we have aromatic rings that are not too strongly deactivated, they will react with an acyl halide in the presence of a Lewis acid to produce an aryl ketone.